everyone, myself Nishitha, Assistant Professor, Department of CSIT, working at MLR Institute of Technology. In previous sessions, we have seen about CPU scheduling algorithms. In this session, we are going to see about process synchronization. So let us see the overview of this presentation. In this presentation, we are going to see about process synchronization. First one is process synchronization, then next critical section problem and what is about Peterson solution and definition of semaphores and different types of semaphores. So let us see our first process synchronization. So in this process synchronization, it is the coordination of execution of multiple processes in a multi-process system. So it consists of multiple processes in a single multi-process system to ensure that they access shared resources in a controlled and predictable manner. So these multiple processes can be accessed with the shared resources. So what are the shared resources? It can process with the different kinds of multiple processes at single shared resource. So that is what about synchronization. Next, it aims to resolve the problem of race conditions and other synchronization issues. So it can raise some of the conditions like a synchronization issues in a concurrent system. Means what? It can solve the problem by raising its condition by providing some synchronization issues in the process. If any error or anything happens, means whatever the error occurs or the issue can be solved with the synchronization. That is what about process synchronization. The main object of process synchronization is to ensure that multiple processes can access shared resources. So the main thing about this process synchronization is nothing but it can access or it can ensure that multiple processes can be shared with shared resources. So without interfering with each other. So while solving, they should not interfere with one process to other process. That is what, without interfering with any other. And to prevent the possibility of inconsistent data due to concurrent access. So whatever the possibility of this inconsistent data, it can be accessed through concurrent access. That is what about process synchronization objective. So to achieve this, various synchronization techniques such as semaphores, monitors and critical sections are used. So what are the different techniques for synchronizations are nothing but semaphores, monitors and critical sections. So on this basis of synchronization, processes are characterized as one of the following two ways. So there are two types for this synchronization process. So what are they? Independent process and cooperative process. What is independent process? The execution of one process does not affect the execution of the other process. Means while execution, only one process can be executed, no other process can affect. So while P1 is under execution, so P2 will be under waiting until P1 completes its execution. No other will affect for P1. That is what independent process, compiling or executing single process at one time. Next, cooperative process, a process that can affect or be affected by other processes executing in the system. So while P1 is executed, P2 can also execute. So that is what cooperating. So based on this cooperation, both can execute at a time. So that is what the difference between independent process and cooperative process. So let us see first problem about critical section problem. So in this critical section, a core segment that can be accessed by only one process at a time. So in this critical section, only one core segment can be accessed with the process within the time. So only one process at a time. The critical section contains shared variables that need to be synchronized. So it consists some shared variables and that should be synchronized to maintain the consistency of data variables. So whatever it is sharing the variables, that should be synchronized and to maintain the consistency of data variables. Data variables are nothing but whatever the variables you are taking. Suppose in a C program, when you are taking numbers, integer, what are the variables? Numbers. That is what some kind of data variables here we are taking. So So the critical section problem means designing a way for cooperative processes. So in this critical section problem is designed to way for the cooperative process. What is cooperative? One process is under execution, another can also execute. That is what cooperative process. To share access to shared resources without creating data inconsistencies. So while accessing shared resources, they should not get any creation of data inconsistency. So whatever it is sharing, it can be under only one data consistency. So no other data inconsistency should occur. That is what about this point. So the critical section problem means designing a way for cooperative process to access shared resources without creating data inconsistencies. So within the data only should create the problem. So let us see what is the do while condition. Do will write the condition, then next while statements. So do, here we are writing some critical section, entry section. Entry section is nothing but critical section. Exit section is nothing but reminder section. So while it is true, this will execute. If it is false, it does not execute. That is about critical section problem. So we are having two sections, that is entry section and exit section. Entry section is nothing but critical section. Exit section is nothing but reminder section. So this is what about critical section problem. Next, how we are going to solve this? In this entry section, the process required for the entry in the critical section. Entry section is nothing but critical section. Exit section is nothing but reminder section. So any solution to the critical section problem must satisfy these three requirements. What are the three requirements? Mutual exclusion, progress and bounded waiting. So what do you mean by mutual exclusion and what do you mean by progress and what do you mean by bounded waiting? So let us see. If a process is executing in its critical section, then no other process is allowed to execute in the critical section. So nothing but when P1 is executing, no other process should enter. That is what about mutual exclusion. So until and unless the process completes its execution only, other process can enter. That is what about mutual exclusion. Next, progress. If no process is executing in the critical section and other processes are waiting outside the critical section, then only those processes that are not executed in their reminder section. So when two processes are under critical, no other process is under critical section, then it goes to reminder section. Reminder section is nothing but exit section. So then reminder section can participate in deciding which will enter the critical section next, and the selection cannot be postpone indefinitely. So until and unless the critical section means entry section, until and unless the process completes only it can exit. Otherwise, until and unless it does not complete its execution, it should remain in the critical section itself. So if no other processes are not executing in the reminder section, then it can participate in deciding which will enter in the critical section next. So until and unless the process completes its execution and comes to the exit section, and then only it can exit. Otherwise, it should be under entry section only until and unless our progress is completed. That is what about this progress requirement. Next, what do you mean by bounded waiting? A bound must exist on the number of times that other processes are allowed to enter the critical sections. So, in this bound must exit the number of times. Bounded waiting is nothing but how much time is the process is under waiting. So, until and unless the time requirement for the P1 it is not completed on time, then it should be waiting. So, that is what about bounded waiting. After a process has made request to enter its critical section and before the request is granted. So, here in the entry of this critical section, until and unless the request raises only, then P2 can enter. Otherwise, it cannot enter. So, until and unless P1 completes its execution on time only, then P2 can enter. Otherwise, it should be under waiting. That is nothing but bounded waiting. So, these are the three requirements for the critical section. What are they? Mutual exclusion, progress and bounded waiting. So, next is Peterson's solution. Peterson solution is a classical software-based solution to the critical section problem. So for this critical section problem, we are solving with Peterson solution. In Peterson solution, we have two shared variables. So we are having two shared variables. What are they? Boolean with the flag of I and int turn. So why we are taking only boolean and flag? Boolean is nothing but whether we need to take two values, either it's 0 or 1 or it is true or false. Whereas int turn is nothing but whatever you are going to take the value in turn. So that is we are taking as turn. So first boolean flag of I. Here initialized to false. Initially no one is interested in entering the critical section. So when the initial value is false, no other process can enter. Why? Because no one process is interested to enter its critical section. Why? Because the condition is under false. When it is true, it is ready for the entry into the critical section. When it is false, it is not interested into entry section. That is what about boolean flag of I when the initialized is false. Next, int turn. The process whose turn is to enter the critical section. So when the process is turn is nothing but when you are taking the turn value, then it changes, it is ready to enter its critical section. So that is about int turn. So here we are writing the condition do open brace flag of I true, then turn equals to j. While we are writing some condition flag of j logical and turn double equals to j. So when it is true, it enters in critical section. When flag of I equals to false, then it enters remainder section. So next, while we are writing true. This is how we are going to solve the critical section problem with Peterson's solution. Next, we hear Peterson's solution preserves some conditions. What are the three conditions? In nothing but in previous critical section also we have seen about mutual exclusion, progress and bounded waiting. Here also the three conditions are applied. So mutual exclusion is assured as only one process can access the critical section at any time. So it can access only one process at any time based on the entry section, that is nothing but critical section. So in progress, it is also assured as a process outside the critical section does not block other process from entering the critical section. So when the process is also assured outside the critical section, then that it should be under block or other process cannot enter into the critical section. Why? Because the condition here block is nothing but they cannot allow or they cannot enter into the critical section. Why? Because that block is blocked. Next, bounded waiting is preserved as every process gets a fair chance. So until and unless the time completes for the process P1, no other process can enter. So after completing its time only, another process can enter. That is what waiting about bound waiting. Nothing but waiting for the entry into the critical section. This is what all the three conditions for Peterson's solution. What are they? Mutual exclusion, progress and bounded waiting. So next, semaphores, one of the most important topic in operating systems. So semaphore is a signaling mechanism and a thread that is waiting on a semaphore can be signaled by another thread. So semaphore is nothing but it is a signaling mechanism where a thread can be waiting on a semaphore and can be signed by another thread. Until and unless the thread can be waiting, the signal can process by the another thread. That is what about semaphore. This is different than a mutex, as a mutex can be signaled only by the thread, that is called the waits function. So here this is having some mutex. Mutex values are nothing but in semaphore we will be having mutex, wait, signal. So whatever we are giving mutex can be as signal. Only one thread can be under some function. That function is nothing but wait function. So a semaphore uses two automatic operations. What are they? Wait and signal for process synchronization. In semaphore we are having two automatic operations. What are they? Wait and signal. So in this, semaphore is an integer variable. Semaphore is nothing but it is an integer variable which can be accessed only through two operations. What are the two operations? Nothing but wait and signal. So let us see the different types of semaphores. So semaphores are two types. What are they? Binary semaphores and counting semaphores. So binary semaphores and counting semaphores. So binary semaphores, they can only be either 0 or 1. So the name itself says binary semaphore. Binary is nothing but 0 or 1. They are also known as mutex locks. As the locks can provide mutual exclusion. Mutual exclusion is nothing but until and unless the execution of the process is completed, next process can enter into the entry section. Otherwise, it cannot enter into the section. That is what about mutual exclusion. All the process can share the same mutex semaphore that is initialized to 1. So all the semaphores can be mutex semaphores and that can be initialized to the value of 1. Then the process has to wait until the lock becomes 0. So until and unless the given value is 1, then after the wait is over, the lock should be and become 0. So when it is 0 only, the process can be released from the waiting section, or else it should be under lock section. That is what about this point. Then the process can make the mutex semaphore 1 and it starts its critical section. So when it is locked, it is becoming 0. Now after again when it is releasing, the mutex semaphore should be 1 and it starts its critical section. Again it starts from the entry section. That is what the value changes, only the process changes. Otherwise it should be under lock condition. When it completes its critical section, it can reset the value of mutex semaphore to 0 and some other process can enter into critical section. So here when they are reset the value of mutex semaphore 0 and some other process can enter into critical section. So when it is under 0, it is blocked. So other process can enter into the critical section. That is how we are going to reset the values of mutex semaphore and how we are going to enter into the critical section and how we are going to release from the lock. These are the binary semaphores. Conditions are reserved for the semaphores. Next, let us see about counting semaphores. So counting semaphores, they can have any value, are not restricted to a certain domain. So they can have any value, no any restricted value can be created for that domain. They can be used to control access to a resource and has a limitation on number of simultaneous accesses. So they can control its access and they can have some limitations on the number of simultaneous access. So number of process will be continuously coming for the execution. So until and unless control of the resource to some extent or to some limitations, then only this process can be handled smoothly, or else the number of simultaneous access will be happening continuously. That is what about this point. The semaphore can be initialized to the number of instances of the resource. So the semaphores can be initialized to n number of instances for the n number of resources. Whenever the process wants to use that resource, it checks if the number of remaining instances is more than 0. So whenever a process wants to use that resource, so suppose P1 wants to use some resource, it checks the number of remaining instances. So number of remaining processes are ready or not, then until and unless then it becomes 0, then only that process has some instance availability. So it checks its number of remaining instances and it should become more than 0, and then only other instance variables can be accessed through that process. That is what about this point. Then the process can enter its critical section, thereby decreasing the value of the counting semaphore by 1. So then the process can enter its critical, when it is entering into the critical section, it can be decreasing the value for n number of counting semaphores by 1. So it should be entering the counting of semaphore by the value of 1. After the process is over within the use of instance of the resource, it can leave the critical section, thereby adding 1. So after the process completes its execution, then the other instance of the resource can leave the critical section. So after execution, it can release from the critical section and it go by exit section, and or else it can add the value by 1. to the number of available instances of the resources. So whatever the available instances of the resources are applied to this process. So this is about counting semaphores. So today's session we have learned about process synchronization, critical section problem, Peterson's solution, and semaphores and types of semaphores. So two types, what are they? Binary semaphores and counting semaphores. In the next session, we are going to see about classical problems of synchronization. In that, we are going to see about bounded buffer problem, nothing but producer-consumer problem, and readers-writers problem, and dining philosophers problem. So, if you have any doubts, you can comment. Thank you.